So we defined connected graph. So for example, let's say you have this graph. This is connected graph. And you have this graph. Both are connected graph. But somehow, how do you feel? This feels more connected than this. We don't know why, but somehow in various problems, we have a different situation. Let's say these are the cities, and then these are the road between them. And in one day, I mean, lots of snow comes, so this road is no longer available. Then now, I mean, this part and this part are separated. But here, even if like some roads are unavailable due to such accidents, it's still connected. So again, it's depending on the formulation of the problem, but somehow we feel that this has to be more connected than this. Indeed, later we will actually formalize this connectivity. We will define which is more connected and which is less connected. But maybe we start with the least connected graph. So we want to first deal with the simple problem, right? From the look of it, this is more complicated graph than this. The structure, it's quite intuitive. You can understand, but here it's more complicated. So we want to deal with the connected graph first, but the connected graph, which is least connected. So how do we formalize this connected graph, which is like minimally connected? So as before, in lots of problem, we assume like this load is no longer available here, or this city is no longer available. So those are the natural situations where this connectivity can be hindered. So a natural way to or to measure this like connectivity with the least connectivity is by this concept. We say a vertex is cut vertex, or an edge which is a cut edge. This is either a vertex or edge whose deletion gives a subgraph with more components than G. So we wanted to define minimally connected, whatever it means. We want to define minimally connected ones. Then probably due to our intuition, if you have a more edges, then it could be more connected, and less edges, it could be less connected. So minimally connected might mean that if you delete some edges, it is no longer connected, or delete some vertices, it's no longer connected. So those are probably the minimally connected graph that you want to study. Although for that, I mean, we need to define this vertex or edges whose deletion introduces disconnected graph. Disconnected graph means it is no longer connected. But more generally, I mean, this is actually more general appropriate concept, which gives more component. So connected graph is a graph with one component. And in general, even if we don't have a connected graph, we delete some edges, leave you more components, and we say that this is a cut edge. And we want to study this. And then our final goal today is to study about the minimally connected graph, which is the graph where every edge is a chord edge. More precisely, it's a connected graph where every edge is chord edge. But before going there, let's prove the following proposition, which shows that the cycles are very important and essential concept in many cases, because there is also connection between cycles and this concept of chord. So if E is on edge of a connected graph G, then G minus E is connected if and only if this E belongs to a cycle. So this provides some way to check whether a given edge is a chord edge. Or equivalently, adding an edge E to a graph H fails to create a cycle if and only if the endpoints of E lie in distinct components of H. So if you have a connected component and in H, if you add an edge between two different components, then it doesn't create any cycle. But as soon as you add an edge within the cycle, within the component, it introduces a new cycle. Because before adding this, I mean, this was in the connected component, means that there is path between them. And then you add this, then it creates a cycle. So these two are equivalent statement. It's easy to see that. So let's prove this. So suppose that this E has two endpoints X and Y. And if G minus E is connected, then there exists a XY path in G minus E. And this with E gives a cycle. So this shows that this direction, and take the other direction. Suppose that E belongs to a cycle. C, say. And to show that the connectivity of G minus E, we choose the two vertices, U and V in G. And then what we want to show, that there is path between them. As G itself is connected, G without deleting E is connected, there exists a path P from U to V. And what's the case? If this P does not contain E, then this P lies in G minus E. So we found the UV path in G minus E. So we are done. And if P contains E. Then we assume that U, X, Y, B appear in this order in P. Say you have a P, U to B. There could be X here, there could be Y here. Possibly Y and B could coincide and V, U and X could coincide. Then what do we know? Okay, so maybe let me draw this way. X, this is E. Then what do we know? This is the one that we delete. But since G minus E contains UX has in P, and then XY has in G minus E, and YB has in P. So this is a UX path. Then there must be XY path in G minus E, and then you have YB path. So concatenating them yields there exists UB walk in G minus E. And we know that the UV walk in G minus E contains the UV path in G minus E. Hence, G minus E is connected. So this provides a relationship between the codex and cycles. Okay. And so our goal again is to find what's minimally connected graphs. And another words, I mean, words, connected graph where every edge is coded. But intuitively, you have a less number of edges, then it is less and less connected. So we want to also study about how many edges does it have. What's the smallest number of edges in a connected graph has? So that also will be related to this question, number of edges in a connected graph. And in terms of that, we can prove this statement. So the number of edges and being connected are related. So if you have a graph with n vertices and m edges, then it has at least n minus m component. So we can prove this. Then this kind of shows that if you want to get a connected graph, then this has to be 1. This has to be 1. No, sorry. It has to be 1 component. So this has to be less than 1. That kind of give you some bounds on the number of edges in terms of n. So how do we prove this? Any such a graph, n vertices and m edges, how do we draw it? You put n vertices and then add edges one by one, right? So any such graph can be obtained from the empty graph by adding an edge by edge. Then what? This starts with n components. And it's each addition decrease the number of components by one, by at most one actually. And this proves the proposition. So you decrease it by at most one m times, then you are left with this many, at least this many components. So this proposition provides some, so this form are good tool to study this minimally connected graph. And you will see this soon. So what this proposition means, this says that every connected graph, which has one component, connected n vertex graph, has at least n minus one edges. Yeah. And this is sharp, meaning that this is best possible. This n minus one cannot be improved to n by an example of, say, Pn, path of n vertices. It has exactly n minus one edges, n vertex path. Okay, then, so what was our question? So, smallest number of edges in a connected graph is what? N minus one. And then there are other graphs which also, graphs other than this path, which also has the smallest possible number of edges. And then those are actually, we will show that those are the graphs with the minimal, those are the connected graph, which is minimal in terms of this being connected. So what are those graphs? Those graphs are actually defined in this way. We say that a graph is a cyclic graph, or we call this a forest. This is a graph with no cycle. And we say that a tree is a connected cyclic graph. And we say a spanning tree in a graph is a spanning subgraph. That is a tree. And maybe let's introduce the definition as well. We call a vertex with degree 1 as a leaf, and a vertex of degree 0 an isolated vertex. So with this definition, we now want to understand about this tree. So this tree is the answer to this question. So we'll show that the trees are the graph where every edge is connected, a chord edge. And these are the graphs which are connected and then have the smallest possible number of edges among the connected ones. So we can prove the proposition about the trees some simple proposition. So every, say, non-trivial tree has at least two leaves. So what does non-trivial tree means? So here, trivial tree is just K1. If you have one vertex and nothing else, so this is, not so interesting. So we forget that. And otherwise, you have at least two leaves. And deletion of a leaf from a tree is a tree with one less vertex. And this provides some recursive structure of the tree, which we can explore it later. And every n vertex tree has n-1 edges. So we can prove. First, trees are connected. We know that all the vertices in trees are not isolated tree. It has degree at least 1. So first, what we do is we again use the maximality. Consider a maximal path. And what? If an endpoint, so you have a path P, or P, say this one, say give a name U has a degree at least 2. Then what happened? By the trick that we saw, either it's sending acid to outside, getting a longer path, which is contradiction, or it comes back. But that's not true because then there must be an HE incident to U and say other than this last edge, it's incident edge in P. Then by the maximality of P, the other endpoint of E is also in the vertexes of this P, yielding a cycle. A contradiction because our graph is 3. Hence, this endpoint and this endpoint of the path are leaf. They have degree 1 because it's not more than 2, and then you know that it is not isolated vertex, then it has to be leaf. So we have 2 leaves. Okay, and that shows 1. And what do we know? And to show the second one, we want to show that the deletion of a leaf of a tree yields a tree with one left vertex. But what do we know? This a leaf, this cannot be a cut vertex of a tree. Why? As if you have a cut vertex, so deleting this leaves more than one component, there must be an edge from this vertex to this component in the original graph. As a cut vertex X of a connected graph G has a neighbor in each component of G minus X. So this is not a vertex. Also, if you delete this, deletion of a vertex does not create a cycle. So G minus a leaf is again connected acyclic graph, a tree, which is a tree. The second one is true. And third one, we want to show that every n vertex tree has n minus 1 edges. And what do we know? By the previous theorem that we proved, no, not theorem, the proposition. So we proved this proposition that here adding an edge fails to create a cycle if and only if the endpoint of E lies in distinct components of H. So what do we know by previous proposition? If you're adding an edge to a graph, it reduces the number of components unless it creates a cycle. But what do you know? Since adding the edges of a tree to n isolated vertices. So you put the vertices first and then you add edges until you get this tree that you have. This does not create a cycle because tree has no cycle. And it ends with one component. So you start with n component, and every time the number of components decrease by one because it doesn't create a cycle, so it decreases by exactly one. Then it ends with one component. That what it means that it must add n minus 1 edges. So this proves that the trees have n minus 1 edges. So what does it mean? So if you have a connected and acyclic, that's 3, and you have n minus 1 edges. So these two together implies this. But we can also show that the other two implies third one. This two implies this two implies this. Of course, assuming n vertices. So any two of them, assuming any two of them, third one comes from. So if G has n, G is on n vertex graph with n minus 1 edges, then this G is connected if and only if G is acyclic. And maybe before proving it, let me mention that again, using this theorem, in this tree, there is no cycle. That means every HE is chord edge because no edge belong to a cycle, so this is always disconnected in a tree. Okay, so let's prove this. So first, say this one. If G is acyclic, then what? Every component is a tree. So any graph is disjoint of component. So it's tree. And if the components have orders, say n1, 2, and k, then what? The number of vertices is same as summation of all ni minus 1. What? This is number of edges in the entire graph G. This is n minus 1 edges. And what? Each component is tree. It has ni vertices, so it has ni minus 1 edges. So this holds, and this is what? Summation of ni is n, and then there are k of them. So k is 1. So it means that it is connected. And we proved the other one. Assume G is connected. So this is connected and n minus 1 edges. But as every n vertex graph with n minus 2 edges with n most 2 minus edge and most n minus 2 edges. It's not connected, it's disconnected. So that's what we know from the previous theorem, not theorem, the proposition. So this is n minus 2, then this is at least 2. So not connected. But you know, every edge of G is a chord edge. So no edge lies in a cycle by the previous proposition. So G is a cycle. So we show that any two of these three conditions imply the third. And lastly, let's prove this theorem, which is useful in many cases. So every connected graph contains a spanning tree. The proof is again easy. By the previous proposition, what do you know? Deleting an edge of a cycle does not disconnect the graph. Deleting an edge in a cycle does not disconnect a graph. So thus what we do? We iteratively delete edges. From cycles in a connected graph. It leads to a cyclic graph. So every time you see a cycle, you delete an edge, you delete an edge, delete an edge, until you cannot. But while in this process, it never disconnects your graph. So your final graph is a connected graph, and which is acyclic because you stop it when it has no cycles and spanning subgraph. which is a spanning tree. And this kind of suggests that the understanding tree is important, because when we are talking about connected graph, and then in lots of problems, forgetting these edges makes the problem only more difficult. So you may assume that you delete some edges and then you solve the problem, then that give you the answer to the original one in many cases. For example, if you have a connectivity problem, if you find the path in the subgraph, then that path is also in the original graph, right? And what this suggests is that every connected graph contains a spanning tree. And then if we know that you can solve the problem on this tree, then you solve the problem on the connected graph. So this could be useful in some dealing with some problems. So yeah, so we learned about this tree. And then any two of these conditions imply the other. And then this tree can be recursively obtained by adding leaf by leaf, because we show that the deletion of a leaf from a tree yields another tree. Another meaning is that if you take a tree and then you add a one vertex and then you add an edge, then that's again a tree. So this recursive structure provides you some understanding of this tree. And maybe we give a name to one more special type of tree. So path is a tree, right? So that was one special tree that we talked. And the ones which are as far from path as possible, this is what we call the star. A tree is a star if it has n-1 leaves, the maximum number of leaves, and one non-leaf vertex. So all n-1 vertices are here, and then one vertex here, and all that is between. Okay, so we have learned about this, passes and cycles, and then we define this connected graph. And then we learned about some theorems related to these passes and cycles and connectivity. And then we defined this tree, which has the minimally connected graph. And yeah, we learned about the properties of this tree. So that's it for today. And next time we will learn about the new concept called matching. Okay, thank you for listening. I will see you in next video.